We're now going to introduce complex numbers. We know when we first started doing square roots, if I said square root of 4, we know that we think of square root of 4 as a number such that the square of that number will equal 4. Basically, the equivalent sentence says square root equals box if box squared is 4. So that means that 2 would work because 2 times 2, 2 being squared, does give you 4. One of the things we realized is if I said square root of negative 4 and I wanted to see what that was, I look at the equivalent sentence, which is box squared has to equal negative 4. So that means box times box must equal negative 4. We can't get the same number times itself to equal a negative because a positive times a positive would be a positive and a negative times a negative. So we would say this is not a real number. But mathematicians would like to use this, and so they want to have square root of negative 4 represent a number. And it's not a real number, so they create what's called an imaginary number. Mathematicians say square root of negative 4 is square root of negative 1 times 4. And the square root of negative 1, think of it as you couldn't come out, so that's going to become your imaginary number. So this will be called 2i. And the definition is that when you have square root of negative 1, that's the imaginary number I. In terms of my get out of jail analogy, square root of negative 4 is square root of negative 1. Then we've got the 2 2's. The 2 2's, the pair breaks out, we get the 2, and the square root of negative 1 isn't real, so some of my students said, think of it as it floats up to the skies, and it's the I, it's the imaginary number. So the square root of negative 1 floats up and it becomes the I, imaginary number. We're only dealing with imaginary numbers with square roots. Based on this, once we have square roots of negatives, we have these imaginary numbers, and we will be able to simplify and include the I. So for example, if I said simplify square root of negative 36, I can simplify the same way we did square roots. I would get the prime factors of 36. And getting the prime factors of 36, 2 goes into that 18, 2 goes into that 9, then 3 goes into that 3, 3 goes into that 1. So I have a negative 1, and then I've got 2 2's and 2 3's. Working the same way I did, out would come a 2, out would come a 3. They broke out. But the square root of negative 1, it breaks out, but it's not a real number, so we call it I. So this is the number 6i. We can do the same thing even if it isn't a perfect square. So I might say simplify square root of negative 50. So again, I would get the prime factors. I'll put the prime factors here. We know we have a negative 1. 50 is 25 times 2, so it's going to have a 2 and 2 5's. So what we have, the 5 breaks out. We have the 2 stuck under the radical, and then the square root of negative 1, as I think of it, it floats up and becomes I. So we can write this as 5i radical 2. And we tend to put the I between the number and the radical because very often if we had written it as 5 radical 2i, sometimes people are sloppy and the radical sign goes over the I, and that would be different. We are going to be able to add and subtract, multiply and divide imaginary numbers, but there's going to be a slight trick with the multiplication. So let's look at multiplying imaginary numbers. Now to multiply imaginary numbers, let's start with I times I. I times I is square root of negative 1 times square root of negative 1. Now in this kind of imaginary multiplication, we don't multiply the signs of the negative. What happens is we think of this in this system that the square root of negative 1 occurred twice, so out comes a negative 1. So in actuality, we are going to define it that when you have I squared, that is defined as negative 1. Normally, when we multiply radicals, we multiply the signs as well, but in this case, we're saying that you had two of the same, so out comes the negative 1. So that's going to be part of our definition, that when you have I squared, you get a negative 1. What that means is before we can multiply imaginary numbers, we have to change them to I numbers. For example, if I said simplify square root of negative 4 times square root of negative 9, the key in doing this is to change them first to I numbers. So square root of negative 4 is a 2I. Square root of negative 9 is a 3I. Now we can multiply just like we would normally with any binomials, and we'd have 2I times 3I is 6I squared. And then we use the fact that I squared is negative 1. So this answer is 6 times negative 1 is negative 6. The rule for this is you must change the radicals to I to imaginary numbers before you multiply. So you must do that before you multiply. Radicals that have negatives under. We'll go on to the next page. Now we're going to look at adding and subtracting. So we're going to add and subtract imaginary numbers. So if I say 2I plus 3I, it's just like we would have done 2x plus 3x. 2 imaginary plus 3I would be 5I. Same with subtraction. If I say 4I subtract 11I, 4i's and negative 11i is negative 7i. We'll deal with division a little bit later, but what we now have is we now can create what's called a complex number. And a complex number is when you put together a real part and an imaginary part of a number. So a complex number is a real and imaginary. An example of a complex number would be 5 plus 3i. I took the number 5 and I added to it an imaginary number. That whole number is called a complex number. But it turns out that real numbers can be written in this complex form. The number 7 is 7 real plus 0 imaginary. And the imaginary number 2i is no real, 0 real, plus 2i. We're not going to get in great detail about this, but these complex numbers are used in physics a lot, and it's because with a real and imaginary part, a complex number can be thought of as an ordered pair. So this would be the ordered pair 5, 3. The number 7 is the ordered pair 7, 0. The number 2i is the ordered pair 0, 2. So it's an ordered pair where the real part is the x and the imaginary without the I is the y. The reason we do this is later on you can see we can then graph like we do with the xy, only we'll call it real and imaginary axes. We can graph complex numbers. So this complex number 5 plus 3i means I go 1, 2, 3, 4, 5 and then up 1, 2, 3, and that ordered pair represents the complex number 5 plus 3i. We're not going to be working with this, but this is where it came about. We're now going to proceed to work with these complex numbers just like we work with our real numbers. So we're going to be able to add and subtract. So for example, I might say, take the complex number 2 plus 3i and add to it negative 4 minus 5i. We just add the real part. 2 and negative 4 is negative 2, and then we add the imaginary. 3i and negative 5i is negative 2i. And we get a result that's a complex number. Just like we can add and subtract, we can also multiply and divide. But let's look at multiply first. So if, for example, I might say, take the number 2 plus 3i and multiply it times 4 minus 5i. A complex number looks like a binomial here, so we're just going to FOIL. So the first gives us 2 times 4 is 8. Then we have 12i and negative 10i. 12i and negative 10i is 2i. And now the last is 3 times negative 5, negative 15i times I squared. But we have to remember that I squared is negative 1. So this is 8 plus 2i minus 15 times negative 1. So it is 8 plus 2i minus a minus plus 15. Now it can be written in complex form, and it's 23 plus 2i. So that's that result. Division becomes a little more complicated because I is really a square root. So if I said divide 10 plus 3i divided by 2i. This problem is really 10 plus 3i, but 2i is really 2 times the square root. And we will remember that we have to rationalize to get rid of the square root. But the way we're going to do that is we're going to use the fact that I squared is negative 1. To do this, we're going to multiply top and bottom by I. So we have 10 plus 3i over 2i. We multiply top and bottom by I over I, which is 1. And now I distribute the I through, and I get 10i plus 3i squared over 2i squared. But the I squared has to become a negative 1. So it's 10i plus 3 times negative 1 divided by 2 times negative 1. Continuing, I see that this becomes 10i minus 3 over 2 times negative 1 is negative 2. But our complex numbers must be written with a real part and an imaginary. So I have to write this as negative 3 plus 10i over negative 2, and then I have to separate. So I have to separate the imaginary and the real. This becomes negative 3 over negative 2 plus 10i over negative 2. But 10 divided by negative 2 becomes a negative 5, and minus over minus is a plus. So the final answer is 3/2 minus 5i. And we call this a plus bi form, because every complex number must have a real and an imaginary part. Now we're going to do the last kind of simplification for complex numbers, where I ask you to simplify after dividing 2 plus 3i divided by 4 minus 5i. We know that I is a square root, so we now have to rationalize the denominator. First step is these are put in parentheses, and now we're going to have to get rid of the I on the bottom. Difference of squares will give us an I squared. We're going to multiply top and bottom by this is a word called the conjugate. It's basically the conjugate is the same expression with the opposite sign. So 4 plus 5i. 4 plus 5i. This gives us, we'll deal with the denominator first. We have 16, this is a difference of squares, these two binomials, minus 25i squared. Again, seeing the I squared, we know that we're going to get rid of any radical. Now we're ready to FOIL the top. 2 times 4 is 8. 12i plus 10i is 22i. 3i times 5i is 15i squared. We're now ready to begin finishing it. The I squareds will become negative 1, so it's 8 plus 22i plus 15 times negative 1 divided by 16 minus 25 times the I squared becomes a negative 1. Now we're ready to make this a negative 15 and combine like terms. So we've got 8 plus 22i minus 15 over 16 minus a minus plus 25. We can see that 8 minus 15 is negative 7 plus 22i divided by 16 and 25 is 41. We've done so much work, we're almost ready. Now we separate over the same denominator. So our last step is we're going to separate, and this becomes negative 7 over 41 plus 2241i, just like that. We now have the answer in complex number form. We call this A plus BI form.